Imagine sitting in a room and typing a message without moving your hands. No keyboard, no voice command, just pure thought. Now imagine someone paralyzed from the neck down suddenly controlling a robotic arm or a computer cursor, using nothing but neural signals from their brain. This is not science fiction anymore. This is brain-computer interface technology, and it is advancing faster than most people realize. Right now, laboratories around the world are decoding neuron firing patterns, the electrical language of the brain. And companies like Neuralink are trying to build direct communication highways between human neurons and machines. The question is no longer whether this is possible. The real question is how far this technology will go, and what it will change about being human. To understand brain-computer interfaces, we need to start with the brain itself. The human brain contains roughly 86 billion neurons. Each neuron communicates using tiny electrical pulses called action potentials. These pulses travel across synapses, forming complex networks that represent movement, sensation, memory, emotion, and decision-making. Every thought you have is a pattern of electrical activity across neural circuits. Every intention to move your hand begins as a specific firing sequence in the motor cortex. A brain-computer interface, or BCI, works by detecting those firing patterns, decoding them using machine learning algorithms, and translating them into digital commands. If specific neurons fire in a certain pattern when you intend to move your right hand, an AI system can learn that pattern. Over time, it becomes accurate enough to predict your intention before the movement even occurs. That signal can then move a cursor, control a robotic limb, or operate a computer. There are two primary categories of brain-computer interfaces: non-invasive and invasive systems. Non-invasive systems, like EEG-based devices, place electrodes on the scalp. EEG stands for electroencephalography, and it measures aggregated electrical activity from large populations of neurons. The advantage is safety. No surgery is required. The disadvantage is signal clarity. Because the skull and tissue dampen and blur neural signals, EEG data is noisy and low resolution. It can detect broad patterns but struggles with precision. Invasive systems are different. These involve surgically implanting microelectrodes directly into brain tissue. This allows detection of individual neuron firing or small clusters of neurons. The resolution is dramatically higher. The signal-to-noise ratio improves. Real-time decoding becomes possible, but surgery introduces risk: infection, inflammation, scar tissue formation, and long-term biocompatibility challenges. Neuralink is pursuing the invasive path. Their approach uses ultra-thin flexible threads, each thinner than a human hair, embedded with electrodes. These threads are inserted into the cortex using a robotic surgical system designed to avoid blood vessels and minimize tissue damage. The goal is to create high-bandwidth neural recording with minimal long-term harm. In early demonstrations, implanted patients have been able to control a computer cursor through thought alone. This works by targeting the motor cortex, the region responsible for voluntary movement. When a person imagines moving their hand, specific neuron populations activate. Machine learning models analyze spike timing patterns, frequency changes, and synchronization across neurons. These models gradually learn to map neural activity to screen movement. But here's where it gets even more interesting. The brain is plastic. Neuroplasticity means the brain rewires itself based on experience. When a patient repeatedly uses a brain-computer interface, the brain adapts. Neurons begin optimizing their firing patterns to make the interface easier to control. In other words, the brain learns the machine, and the machine learns the brain. It becomes a feedback loop. This bidirectional adaptation is critical. It means that BCIs are not static tools. They evolve with the user. Over time, accuracy improves, latency decreases, and control becomes more natural. For paralyzed patients, this could restore independence. For amputees, robotic limbs can eventually feel intuitive. There is also sensory feedback research. Some BCI systems stimulate the somatosensory cortex, allowing artificial limbs to send signals back to the brain. Instead of just moving a robotic hand, users can potentially feel pressure or texture. This requires precise stimulation patterns that mimic natural neural encoding of touch. If successful, this closes the loop between intention and sensation. But brain-computer interfaces are not limited to motor control. Researchers are exploring memory restoration, depression treatment, and seizure prediction. In epilepsy, abnormal electrical discharges can be detected before a seizure occurs. Implantable devices can deliver targeted stimulation to interrupt the seizure before symptoms appear. This is already happening in experimental clinical trials. There are also attempts to decode speech directly from brain signals. The speech motor cortex activates when we speak and even when we silently imagine speaking. By training AI models on neural data paired with spoken words, researchers are beginning to reconstruct intended speech from neural activity alone. This could allow locked-in patients to communicate naturally without typing letter by letter. However, decoding thoughts is far more complex than decoding movement. Movement signals are relatively localized in the motor cortex. Thoughts, memories, and abstract ideas involve distributed networks across the brain. Neural representation is not stored like text in a file. It is dynamic, context-dependent, and influenced by emotional and sensory states. So while headlines talk about mind reading, current technology decodes specific trained signals, not spontaneous private thoughts. One of the biggest scientific challenges is signal stability over time. When electrodes are implanted, the immune system responds. Glial cells form scar tissue around foreign objects. This can degrade signal quality. Engineers are working on biocompatible materials, flexible electrodes, and wireless transmission systems to reduce long-term damage. Another challenge is bandwidth. The human brain processes massive parallel information. Current BCIs capture a tiny fraction of total neural activity. Scaling up requires thousands or millions of channels. That demands advances in microfabrication, power efficiency, wireless communication, and data processing algorithms. Ethically, this technology opens enormous questions. If neural signals can be decoded, who owns that data? Could governments demand access? Could companies monetize thought patterns? Brain data is fundamentally different from browsing history or biometric scans. It reflects intention and internal states. Regulation will be essential before consumer-level BCIs become widespread. There is also the enhancement debate. Today, BCIs are focused on medical restoration. Tomorrow, they could enhance cognition, faster information retrieval, direct AI integration, instant translation between languages, even memory augmentation. But altering cognitive processes raises philosophical questions about identity. If your brain is partially integrated with an AI system, where do you end and the machine begin? Technically, merging AI with neural data would require real-time encoding and decoding of multi-regional neural patterns. Advanced neural networks could interpret high-dimensional firing sequences. Closed-loop systems could stimulate specific circuits to enhance focus or suppress anxiety. But long-term effects on brain plasticity are still unknown. Another frontier is distributed brain-to-brain communication. Experiments have already transmitted simple signals between two brains, using non-invasive stimulation and EEG decoding. The bandwidth is extremely limited, but conceptually, direct neural communication is possible. Whether this evolves into practical technology remains uncertain. From a physics perspective, neurons operate through electrochemical gradients. Ion channels regulate sodium and potassium flow, generating voltage changes across membranes. These electrical changes are what electrodes detect. Precision requires understanding the biophysics of membrane potentials and synaptic transmission. Advanced BCIs rely on accurate modeling of spike timing and firing rate modulation. The machine learning side is equally complex. Neural decoding uses recurrent neural networks, convolutional models, and probabilistic state space models to interpret time series data. The system must differentiate between noise and meaningful spikes. Training requires calibration sessions where intended movements are paired with recorded neural data. Despite the challenges, progress is accelerating. Advances in AI dramatically improve decoding accuracy. Improvements in materials science enhance electrode longevity. Robotics improves surgical precision. Interdisciplinary collaboration between neuroscience, electrical engineering, and computer science is driving rapid innovation. In the near future, BCIs will likely remain medical devices, restoring mobility, treating neurological disorders, providing communication for patients who cannot speak. But in the longer term, integration with augmented reality, virtual environments, and AI assistants could redefine computing itself. The smartphone replaced the keyboard. The touchscreen replaced the mouse. Brain-computer interfaces could replace the interface entirely. The question is not whether we will connect brains to machines. That process has already begun. The real question is how society manages the transition. Regulation, privacy protection, ethical boundaries, and equitable access will shape whether this becomes liberation technology or a new form of control. Science fiction often imagined telepathy, cybernetic upgrades, and neural networks linking humanity. Now those concepts are moving from fiction into clinical trials. The brain remains the most complex object in the known universe, Yet we are beginning to map its signals, decode its language, and interface with it directly. If progress continues at its current pace, the next decade could redefine human-machine interaction. Thought-controlled computers may become normal. Paralysis may no longer mean permanent immobility. Communication barriers may shrink, and perhaps the most profound shift will not be technological, but philosophical. When thought itself becomes input data, the boundary between mind and machine will blur. This is not the distant future. It is happening now, and we are only at the beginning.